History students. This is Mrs. Talley, and this is my assistant Carter, who's been going through the quarantine with me. I think his new mission in life is to try to get me to play Magic of the Gathering.
Yes.
Because he has been missing that game with his school friends, but as of right now, he is my assistant, helping me to get you guys through your Block 2 Assignment 1 on the Carbon Equilibrium Challenge. So I'm going to try to talk you through this assignment to make it a lot easier. So listen to these videos, and by the end you should be able to complete this assignment. And I'd also like to thank my husband for being our video producer on this video. So thank you, Johnny. Mr. Talley.
The first question we need to answer is, what is equilibrium?
Hey, Mom, want to play Magic together?
Carter, you said you were going to help me with this. Come on, let's do this. We're going to teach them about equilibrium. Okay, we can play that later. Put the cards away. Okay. All right, so our first concept that we need to learn is equilibrium. So what equilibrium means is that the rate of the forward reaction is equal to the rate of the backwards reaction. So right here we have a reaction, and Carter, I think you mixed the cards because he has the products on the wrong side.
Oh, okay.
So let's flip those real quick.
I'm sorry, that was filming from that angle.
It's okay. All right, so we start a reaction with reactants on one side and products on the other. And you guys are used to seeing just one arrow in the middle. Reactants make products. But in most reactions, they are actually going in both directions. Okay, so they're going in both directions. So you have reactants making products at the same time that products are making reactants. This is almost like photosynthesis and cellular respiration. So in equilibrium, so you notice we have two piles of pennies right here. So we already have some products made and we already have some reactants. So for equilibrium, we want the rate to be the same forward and backward. So Carter's going to do the forward reaction and I'm going to do the backwards reaction. So if we each do one penny at a time, you'll notice that the piles stay the same. So the forward reaction and the backward reaction are going at the same rate. But what would happen if the backwards reaction goes faster than the forward reaction? So let's try it and see what happens. So the backward reaction is going at a faster rate. So you should notice that the reactant side is building up a lot more pieces, okay? But then what if we went the other direction? What if the forward reaction went faster than the backward reaction? So let's try it. So you'll notice the products are starting to build up faster than the reactants. So hopefully that explains equilibrium.
The next two questions that we need to answer are, how does carbon move between the spheres of the Earth, and what prevents carbon from building up in the atmosphere?
Hi, Mom. What you doing?
Well, I was trying to explain to my students how carbon moves between the spheres of the Earth.
What's a sphere?
Well, a sphere is like a system on Earth, and there's different spheres on the Earth. Like there is the atmosphere, which says right here, and that means like the air. And then the ocean is a part of the hydrosphere, because hydro means water, right? And then animals and plants, they're part of the biosphere, because bio means life. And then like the ground is a part of, you can call it the geosphere, okay? So that's kind of what we're talking about. Yeah.
How does carbon move between the spheres?
Okay, so we know that plants, they go through that process called what? Do you remember? Photosynthesis. So plants, when they go through photosynthesis, they take in carbon dioxide, and carbon dioxide has carbon. So when a plant goes through photosynthesis, it's going to take some of the carbon out of the atmosphere. So all these pennies represent carbon. So it's going to take some of the carbon dioxide out of the air to use for that process of photosynthesis to make some sugars. Okay, but plants also go through cellular respiration. So they're going to give out carbon in the form of carbon dioxide to the atmosphere. And then animals, do they do photosynthesis?
No.
No, they don't. They just do cellular respiration. So we're going to take a penny or carbon from the animals and it's going to go into the atmosphere. So you notice plants are doing this and animals are putting carbon. Are they taking it in though? No, they're just putting it into the atmosphere. Okay. And then the ocean, it can do the same thing. So let's say there's a bunch of carbon dioxide making pressure on the ocean.
Yeah.
So the ocean can actually dissolve some of that carbon dioxide and uptake the carbon. And then it can actually go in the same way. So if there's lower pressure out here, the carbon will undissolve and go back into the atmosphere. So that's kind of how carbon moves between the atmosphere.
What happens when too much carbon goes into the atmosphere?
Okay, so let's say there's not very many plants uptaking the carbon and the animals are in overdrive. So they're breathing out like crazy and just dumping carbon into the atmosphere. So what does the ocean do? Well, it's really cool. These spheres act like a big giant feedback loop. So one stimulus to one will act as a kind of a trigger to push carbon into the other sphere. So the ocean is actually really important. It holds a bunch of carbon. So let's say there's all this carbon dioxide in the air, that's the carbon. So it's putting pressure on the ocean. So guess what the ocean can do? It can dissolve, because carbon dioxide is soluble, it can dissolve a bunch of that carbon dioxide. Well, then let's say that there's not enough carbon in the atmosphere in the form of carbon dioxide. So then the ocean, what it can do is it can regulate that. So this is a lower pressure. So this carbon dioxide can undissolve and come back into the atmosphere. So it's really cool. Our world is very cool at regulating and keeping the carbon in equilibrium. So your challenge is going to be to design a country that is actually carbon neutral, where this whole process is in equilibrium. And I'll go over that in just a little bit.
The last thing that I will explain is the task, how to complete the carbon equilibrium challenge.
All right, now that I've given you the background information on the carbon cycle and equilibrium, now you're wondering, how do I actually do this assignment? So if you look at the carbon equilibrium challenge, we've kind of already gone over the background. You're going to look to the part where it says your task. So it says you're going to design a country that has a neutral carbon status. So in order for something to be neutral, the amount of carbon going in has to be the same amount of carbon going out. Okay? It also says you're going to choose the basic statistics and parameters for your country, such as the climate, okay, because different climates have different kinds of trees. The economy, so some countries produce more CO2 per person than other countries just based on how many cars they have and that kind of thing. And then also the size of the population. And it gives you a reference table that you can use in order to kind of figure out the number of people and then how much metric tons of CO2 they use per year. Okay, then you're going to look on the back, and it's also going to give you a table that's going to give you types of forests and how much those forests can uptake in CO2. All right, so let's go through the checklist. So the first thing you need to do is pick the basic parameters of your country. So my country, I'm calling it Tallyland because my name's Tally. And it's going to be a place that has a temperate forest. And I'm going to say that it has 50 million people. And I'm going to say that each person is going to give off 4.2 metric tons. So I just made up these numbers. Okay? And then the next part says, so give it a unique name. All right? And then it says, show the calculations for the total CO2 emissions for your country. Okay, so how do we do these calculations? So I'm going to represent this with pennies just so you guys can see this. So 1 penny is equivalent of about 10 metric tons. So I said in Tallyland, we have 50 million people. Okay, so here's how we do the first calculation to see how much CO2 Tallyland people produce. Okay, so we have 50 million people, and what we're going to do is we're going to multiply that by the metric tons per person. So on mine, I said that there is 4.2 metric tons of CO2 produced per person. So
If you notice people here, person here, these cross out because you can cross out those units. So all you got to do is take 50 times 4.2 and you get an answer. So if you take 50 times 4.2, you get 210 metric tons of CO2 produced. So if I have 1 penny for every 10 metric tons, I put 21 pennies right here. So I need to make sure that these 21 pennies are balanced out by the ocean and by the plants. Okay, so let's do the next calculation. So how much are the plants going to need to uptake? And so that'll help me figure out how many plants I need. So what I'm going to do, so I know that the ocean, if you read in the first part, it said that the ocean can take in 30%. So that means the plants can take in 70%. So let me move this out of the way for a second. So I'm going to take my 210 metric tons of CO2 and I'm going to multiply that by 70%. And 70% as a number is 0.70. And once I do that calculation, I get 147, so I'm taking this number, 210 times 0.7, and that's going to equal 147 metric tons of CO2 produced. So that's how much needs to go into the plants. So to represent that, I'm going to have about 15 pennies. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So how much does the ocean need to take in? About 60 metric tons. So that's what those pennies represent. So if the ocean takes in 60 metric tons, we put out 210 metric tons, then the plants need to uptake 150 metric tons. But how many trees is that? So we're going to go to our next calculation. All right, so you're going to take the number of metric tons from the trees. So you're going to put up whatever your number is. So mine was 147 metric tons of CO2 produced. And then what I'm going to do is I'm going to multiply that by 1 hectare, okay? And I'm going to divide that by 4.6 metric tons of CO2. Now you're asking, where is Mrs. Talley getting these numbers? So what I'm looking at is on my Carbon Equilibrium Challenge, I look at the temperate forest. So it says a temperate forest can sequester or take in 4.6 metric tons per hectare per year. So that's 4.6 metric tons of CO2 per hectare. So you'll notice metric tons of CO2 and metric tons of CO2 can cross out. So how do I do this calculation? I take 147, multiply by 1, divide by 4.6. And then my answer is going to be roughly, because I rounded, 32 hectares of forest needed. Okay, but how many trees is that? So you're going to look back on your table and it says that in a temperate forest you have about 350 trees per hectare. So let me get rid of this and we're going to move this to here. Okay, so we have 32 trees per hectare. Okay, so this is trees, so I want trees to go right here. And, oh, I need to get the hectare again. Okay, so this is hectares, so hectares needs to be on the bottom. So this calculation will be 32 times 350, because that's how many hectares I need times the number of trees. And so that will be 11,200 trees is how many I need. So in order to uptake 150, roughly, metric tons of CO2 in Tallyland, I need 11,200 trees. Okay, so now the final part that you're going to do is you're going to show the calculations, and you're also going to take an 8.5 by 11 sheet of paper, and you're going to draw a representational map of your country showing these amounts moving around. And you can use something like I did to represent metric tons, or you can just draw arrows and say this many metric tons is moving from here to here in order to keep it neutral. I hope you enjoyed this video and this made sense to you. Thank you.